Hi, this is Aaron Jerome, Jerome Electronics. I just wanted to say a few words about how to use a multimeter. This multimeter is probably a little more, advanced, costs more. I like my students to understand that multimeters don't have to cost a lot. I mean, you can get them for $6 at Harbor Freight as of the making of this video. And so I actually use the Harbor Freight multimeters in my classroom. So that's what I'm going to explain here as well. The ones at Harbor Freight are red, but basically I think they're all Chinese and they work. And so they're cheap and we can use them. But a lot of students are a little bit confused about how to use them. So this on the screen, this is a basic circuit. We're using a Nuki bat to run some electrons through a little lamp. And of course, they have to go back down into the Nuki bat to make a complete circuit. And so we can use a multimeter to check this circuit for voltage, amperage, and resistance. First thing to know is, where do you plug in the wires? So, first thing you need to know is that the black wire always plugs into the hole, and the hole is labeled COM. And COM is an abbreviation for common ground. So the COM is always the ground. Now, why the black wire? Is there something special about the electronics of a black wire? No, it's just the color. The red wire will work too, but the color is, we're actually respecting the convention that black goes into COM. So when we see it, we know that the black ground is common, and the red wire is going to be the power wire where the electrons will, source from, depending on how you interpret that. So this means that the red wire goes into the connection. Most often it goes into the correct connection that has the V, the omega, and the MA. I call it the V omega Ma connection, but V stands for volts, and the little horseshoe omega stands for ohms, and then MA stands for milliamps. This range will measure milliamps, but doesn't quite get into the full amps, but milliamps is the most common. We don't need full amps for little electronic gadgetry. And so in this class, we never get into anything that's just a few more than milliamps. Okay, so then we need to set the dial to whatever we want to measure. There it is, the V omega Ma. Well, if we want to measure voltage, we would set the dial to the direct current voltage range. We probably won't use alternating current because those are greater currents, greater pressures, greater voltages, which can drive more electrons, which can be dangerous. And in a class like this, we don't need any dangerous circuits. I mean, they can be built, but we don't necessarily need them to understand how electrons flow and what electronics is. So we will set the dial to somewhere in the DCV range. Now, there are 5 different ranges you could choose, and I'm going to talk about those as well in just a moment. But let's talk about also, if we want to measure amps, we will turn the dial to one of these 4 DC amp ranges, direct current amp ranges. Or if we want to measure ohms of resistance, we can turn the dial to one of these ohms settings, I guess that's the best way to say it for now. I guess the big question that students have right now is, why do we have to have several ohms ratings and several volts several ohms ranges and several volts ranges and several amp ranges? I've got a kind of a story, an illustration to help you figure that out. It seems way out in left field, but stay with me, and I think you'll understand. Okay, so let's say you have a unicycle, and you want to know how fast you can go on your unicycle. So you put a speedometer on your unicycle, And what is the speedometer? We want it always to start at 0, right? But how fast can a unicycle go? What is the maximum speed for a unicycle? Well, it might be different if you're going downhill with the wind against your back, but the normal maximum, I wouldn't say that you could actually get much more than 20 miles per hour. So here is or even 10 miles an hour. So here is a nice speedometer that we can put on our unicycle. Now, think about this for a minute. How useful would this speedometer be if we used it on something really, really fast, like the space shuttle? The speedometer goes from 0 to 10 miles an hour. How useful would that be on the space shuttle? How fast do space shuttles go? Well, I guess they generally cruise at about 17,500 miles per hour. Is it safe to say that this unicycle speedometer would be pegged in the first few seconds of liftoff, and then it would be useless for the rest of the trip? So what I'm saying here is we would want a speedometer that suits the range of the space shuttle, because this one is worthless after 10 miles per hour. So this is not the most accurate range. It does start at 0, it goes to 10, not the most accurate range. Now let's look at the opposite situation. Let's say we were at the speedometer store, and we were looking on the different shelves, and the only one we could afford was this old used space shuttle speedometer, and so we put that on our unicycle. How useful would this be? Well, the speedometer goes from 0 to 20,000 miles per hour, and well, think about it. The dial would probably never really ever leave the 0 mark. So we have a different speedometer range for different applications for different speeds. A space shuttle is exponentially faster than a unicycle. So we want a special speedometer. They both start at 0, but we want one that actually fits the range of velocity for a space shuttle, if that's what we're using for, or the range of velocity for a unicycle to get the most accurate reading. Otherwise, that either the needle will always be pegged at the maximum speed, or it will never actually quite get off the 0 speed. And that's a little bit like these multimeter ranges. Okay. So what we want to do is, and generally what I suggest to students is, if you expect a certain voltage, go to that range. So the DC voltage here has 200 millivolts. That would be 0 to 200 millivolts, or 2,000 millivolts, which is the same thing as 2 volts. And this would be what? 20 cents of a full volt. Here's 20 volts here, 200 volts and 1,000 volts direct current range. What would we expect? Well, it depends on the application, but we want the most precise reading in the window. And to get the most precise reading in the window, we're going to have to find the most precise speedometer or voltage meter to use. Okay? So now we're going to connect our multimeter, and what we're going to do is connect amps in series. Okay, so we got our power supply, our power generator, a Nuki bat, and it's going to power this motor. And so we want to know how many amps the battery is providing to the motor, because maybe we want to increase the amperage, or maybe we want to know if it is actually giving a flow of electrons. So what we have to do first is turn the dial to amps. Now in this case, we're going to use the 10 amp dial. We know we're not going to go over that. This 10 amp connection, this 10 amp port, does not have a fuse on it, but it's also useful for measuring amps, and sometimes it can be used when the other middle port, where the volts omega and and milliamps. Sometimes I found that doesn't work. Okay, so we're going to hook it up, and so we're taking a connection from the top port there, the 10 amp port, connecting that to the battery. The battery is being connected to the motor, and the motor is being connected back to the multimeter. What that means is that every electron is going to go through the motor, but then every electron will also go through the multimeter to be counted. You can't count all the electrons if all the electrons don't go through the meter. So every electron must be sent through the meter, which means amps have to be connected in series in order for the electrons to be counted. So consider this for a moment. This is we're going to talk about voltage next. So why not look at this tire? Think for a moment about this tire. The tire's filled with air, maybe about 45 pounds of pressure. If we want to check the pressure of the tire, do we need to take all of the air out of the tire? No, we just take a sampling of the air, and that tells us the pressure. So think about this. Do we have to actually check the pressure at a specific location? Or can we check the pressure and expect to find the same pressure at any location on this tire? Well, it turns out that we only need a small sample, but it doesn't matter where we take the sample from, because what we're doing is checking how pressurized the air molecules are, not counting the actual air molecules. That's so pressure can be measured from a small sample. All of the air is not needed, and the same is true for electromagnetic pressure or volts. Okay, so when we do this, we can connect for volts in parallel, and one pathway is going to power the motor and make it go, and then we're going to provide an alternate pathway to collect a small sample of electrons where we will check the pressure using the multimeter. So if we want to connect for volts, if we want to measure volts, we connect a different way. Here we've got the circuit. This battery can drive this motor without doing very much, without actually, I guess, doing whatever it can, but it doesn't need the multimeter to power this. Well, we do need to turn, if we're going to measure the volts, maybe we want to see, these motors, they take about 9 volts. So if we want to measure how many volts are going, or volts of pressure in this circuit, we would expect to use the 20 DC volt range. And now what we're doing is creating an alternate path for a few electrons to follow, and then we can measure the pressure of those electrons. And of course, the pressure of those electrons is going to be the same as the pressure of all the electrons, because the pressure should be about 9 volts to make this motor turn. Okay, so doing it again, this time we're going to connect for amps. And remember, to count the amps, we have to count every amp. That blue thing in the lower right corner there is a hydrogen fuel cell. It can generate electrons, and the electrons it generates can also power this motor. And to measure the amps, we got to turn the dial back over to amps, and then we're going to hook the motor up and hook the motor to the multimeter. But remember, this is the same path. Every electron has no choices. There's a single path for all electrons that goes from the fuel cell to the motor, into the multimeter to be counted, back out of the multimeter, and back into a complete series circuit, meaning there's only one pathway, because every electron has to go through the multimeter in order to be counted. All right, let's check the volts. Well, we don't need to connect to the volt. We don't need every electron to go into the voltmeter. We do need to turn back to the range that we expect the voltages to be in. So here we are. There's the alternate path, and we take a small sample of volts down this alternate path, a parallel path. And the rest of the electrons can go through to power the motor. And so that's what we're doing. We're just sampling a small collection of electrons. We can do the same thing with a solar panel. This is a solar panel. We're going to connect for amps. So we have to turn the dial to amps, and then we connect in series, a single path. Every electron goes through the motor. Every electron goes through the multimeter to be counted. Of course, when we count these, we're not actually counting every electron. We're counting groups of electrons called coulombs. And we talked about that in an earlier presentation. Okay, we can also check the volts, but that means we only want a small sample and an alternate path to collect a few electrons to measure the pressure of a few electrons, kind of like what we did with the tire. So hopefully you get the idea. Here's a breadboard. We're going to actually power this motor, and we're going to connect it to the breadboard because we don't want to have to solder the prototype together to see that it actually works. We got a Nuki bat. We're hooking that up. And remember, the Nuki bat, it connects, and underneath it connects across this row. So now it's connected to the motor, and the motor has a wire that comes out, and it's going to this row, all connected underneath, going back down. So what we have here is a series circuit. Well, the motor's not moving as fast as we like. This Nuki bat maybe has 1.5 volts, and the motor kind of wishes it would have somewhere between 0 and 9 for various speeds. So we're going to add some more voltage. Of course, maybe you remember in an earlier video that to add more voltage, you are going to connect another battery in series. So here's another Nuki bat, and we're hooking it up to its own row on the breadboard, and the power is on one row. And remember, they're not connected vertically. These holes are only connected horizontally. And so what we want to do is connect these in series, because in the earlier video, the series ramped up the voltage. That means we need a single path for electrons. To make that, I'm going to connect positive to negative on the two batteries, and I'm going to lengthen this green bridge so that it is going to the negative of the bottom battery. And if you follow that, you can see there is a single pathway for electrons to flow through this circuit. Okay. If we want to add another battery, we could do the same thing and connect the negatives to the positives and lengthen the return bridge wire. And again, we have it. Now, here we had 1.5 volts, 3 volts, and 4.5 volts. We could continue adding more until we got close to 9 volts. We wouldn't want to go over 9 volts. That's probably too much for this little electric motor. Okay. Well, it's kind of hard to hold those wires onto the batteries, though. That's why battery holders are so popular. Battery holders hold batteries together in series. There's one right there, and it actually is hooking there's 3 batteries in there. Looks like I got the batteries from Kirkland on this on Costco. But this little holder also puts negatives to positives to increase the voltage of the battery. So all we have to do is hook it up for a series circuit. Now we want to check this. We want to check the voltage, and checking the voltage means we're going to take a small sample and run it through the multimeter. Voltage pressure is checked in parallel so that the electrons can either choose to go through the motor or choose to go through the multimeter. So here is my alternate path, and I'm connecting it to the middle port of the multimeter this time, and I'm also giving it a parallel return path. So the batteries are one parallel branch, the motor is another parallel branch, and the multimeter is a third parallel branch. And we have to turn the dial to the 20 volts again to be able to read what we expect to be, in this case, about 4.5 volts. Now we're going to check the running amperage. The amps, that's the count of electrons. We have to hook it up in series. So now this is still parallel. No choices. Series is no choices. But there is a choice. The electrons can come Well, they can come from the battery and choose either to go to the multimeter or to go through the motor. And that's parallel. We need this to be series where the electrons will only go through everything. So to do that, we just go to another row of the breadboard. We're going to move that wire down one row, and move that wire down one row. And now we have a series circuit where every electron must go through every component. Okay. So now we're going to check the amperage. To check the amperage, we're going to have to turn the dial over to one of the amperage ranges. We've chosen the 10 amp position. And we need to move the red wire then to the 10 amp port. And that will measure the coulombs of electrons that are flowing through this circuit. So we can measure the amps. How much power are the batteries giving? Well, if we know the volts, which is 1.5, and it turns out that wait a minute, that's 3 batteries, so that's 4.5. And the amps, since the batteries are connected in series, the amps are 0.4. They do not ramp up the amps because the batteries are connected in series inside that battery holder. So if we want volts, we have to go, or if we want power, watts, we have to multiply the volts times the amps. So the volts is about 4.5 with the 3 batteries in series, and the amps is going to be 0.4. It doesn't ramp up. It's always the same number of electrons flowing through all this. So 4.5 times 0.04. What is that? Okay, well, I don't know. It's about a little less than half of, I don't know, what would you call that? Quick, I wish I had thought to pull here it is. I've got my calculator. Okay, so we have 4.5 volts times 0.4 amps. So I got 1.8 watts of power, because watts is volts times amps. Okay, so we got 1.8 amps here. That's all I've got to say, I think. Let me see. I don't think there's anything else. Oh, that was it. Thank you for listening. Got more videos coming, but this one was how to read a multimeter. Thank you for listening to it. See you next time.